When we determine molecular polarity, we were talked about bond polarity. Now, if you have multiple mixed bonds, some of them are polar, some of them are non-polar, we have to also take into consideration the geometry of molecule or the shape of the molecule. So to understand the shape, to predict the shape of small molecules, larger ones it gets more complicated, but for small ones we can do it. We have to understand concept of their electron groups. Electron groups are not just bonds. They also lone pairs. So electron groups are any group of electrons. Basically, if you have a bonding pair, that would be single or double or a triple bond, or if you have non-bonding pair, that's going to be a lone pair. These are your electron groups. If we look at the number of the atom, that's given and determine the type of the uh, electron group. So for number one, for carbon number one, this is a bond. Just a second. This is carbon 1. So we have to look what it forms. It has 1, 2, 3, and 4. It actually has 4 electron groups. Now I'm going to erase this so we can do the another one. So carbon 2, we have 1, 2, and 3. It has 4 bonding pairs of electrons, right? So 2 of them are 4 together in a double bond. So we are considering these like one. That's why there are 3 electron groups around the carbon number 2. So 3 electron groups. So basically, you think about electron groups like an area where electrons are concentrated. So we have one bonding pair on the left, one on the right, and then those these double bond right here creates a third one. Okay, and now the next carbon is going to be carbon number 3. And we have to look, it has 1, 2, 3, and 4. So it has 4. The next one is carbon number 4. And here we have 1, 2. Do you see that I'm saying what it's a triple bond, but they are together. They are all localized in the same place, so it's 2 electrons groups here. Now for atom 5, which is nitrogen in this case, is where I need you to pay attention. We have 1, but then we have this lone pair that also a group of electrons. So we also have 2 groups for nitrogen. For oxygen on the top, that's now atom number 6. We have 1, 2, and 3. So yes, we have 3 electron groups around oxygen. For atom number 7, there is only 1, so that would be 1. Hopefully it makes a little more sense to you what electron groups are. You're just counting how many lone pairs and how many electron groups are around a specific atom. Also, to determine shape of the molecule, you have to be able to draw a loose dot structure of the molecule and include all of the lone pairs. Again, you want to know that if you skip the lone pairs, you wouldn't be able to correctly count the electron groups, and then you wouldn't be able to predict the shape. And then we are going to lastly use the valence shell electron pulse repulsion theory, which is VESPER. And in that theory, think about this. So let's say I'm talking about electron groups around carbon 2 in the example above, right? So we have one electron group, 2, 3. The shape is not a coincidence that it's I'm just the shape is trigonal planar. The reason why it is like this, because this pair of electrons and those electrons right here, they are negatively charged. And remember, what negative charges, they repulse each other. They repel each other. I'm sorry, they repel each other. So in order for them to stay as far from each other as possible, they are going to assume this uh, trigonal planar shape, right? They are not going to be like this. They are not going to be close to each other, because that's going to create a lot of repulsion between them. And it's also empty space here. So they are going to distribute themselves to minimize the repulsion. And that's why the theory suggests this. So now you can see, for example, here we can look at different shapes and different names. So if you have a central atom, with only 2 electron groups around it, it's going to be linear shape. It's going to be a linear shape here. I'm sorry. The most beneficial with the least repulsion are between 2 electron groups. They're not going to be like this. So if let's say my carbon in carbon dioxide, it's not going to be like this, because between 2 electrons group there are a lot of repulsion, and they stay in a space to minimize this repulsion, to spread like this to minimize the repulsion. So that's why it's linear structure, linear shape. It doesn't matter that oxygen has 2 lone pairs, because it's not a central atom here. We only care about the atoms that connects all them together. That's central. It's carbon here, because in that case the central atom must keep all of the other atoms intact, right? So only the central atom matters. If it has lone pairs, so it doesn't have lone pairs there in this carbon structure. So let's do concept checking. Methane. In methane, there is a carbon which bonded with 4 hydrogen here. This is Lewis dot structure. So hydrogen around carbon, and remember each hydrogen brings one electron here. So they're going to bond, forming four single bonds. So number of electron groups around the central atom. Carbon is my central atom here, and it has 1, 2, 3, and 4 groups. So number of electron groups is 4. Zero lone pairs, electron group geometry. So we need to look at this chart, and it gives us tetrahedral shape of electron group geometry, and so the molecular shape will be the same because four electron groups gives us four bonds also. Tetrahedral. Okay. Um, let's do another one. It's NF3. It's going to be nitrogen surrounded by 3 fluorine. For nitrogen it has 4 valence electrons, and for fluorine it has 7. So there are 3 bonds here between nitrogen and fluorine. So remember, all electrons should be paired. So we have 1, 2, and 3 bonds here, but this is our Lewis dot structure. So the central atom is nitrogen. How many electron groups it has? It is 4, because with 3 bonds it has additional lone pair. So I'm going to put 1 lone pair. So electron group geometry will be tetrahedral, but molecular shape will be different. However, it's going to be pyramidal. And let me explain what that means. So this is my pyramidal shape. Think about this. This lone pair right here repels the rest of them, So this is my nitrogen. It's going to push my fluorines to the bottom, this lone pair, and this flowing in the center. It's not really in the middle. It's kind of, um, um, I'm doing this wedge to show you that it's perpendicular to the paper, so to the screen, so it's actually sticking out and looking at you. It's all the same distance from all the other lone pairs or fluorines. So this is pyramidal. The arrangement of electron groups was similar to this. That was fluorine, lone pairs. We say that the electron group geometry was tetrahedral here, but the shape, because of the lone pair, you can see the shape turns out to be pyramidal. Now the next molecule is oxygen difluoride. Oxygen is in the center. It has 6 valence electrons. Fluorines, as we discussed, each has 7 electrons here. None of them should end up with unpaired electrons. So we know that fluorine is going to form bond here and bond here, and my oxygen then has 2 bonds as it requires. Okay, so again, we have 4 electron groups here. 2 of them are bonds, and 2 of them are lone pairs. So think about the electron group geometry. We have again tetrahedral. This one is a lone pair, this one lone pair too. That's fluorine, that's fluorine, and that's fluorine. So the form of electron groups geometry is tetrahedral, but the shape of molecule is going to be in a different. So with two lone pairs and two bonds, the shape will be bent. So why this is different between electron group geometry and molecular shape? Because because we cannot see lone pairs.